Hello everybody, and welcome to the Office edition of Advent of Code in Kotlin 2024. It is day 6, and you can probably tell that we're in a slightly different place here. That's not a virtual background. I'm in the wonderful Munich offices from JetBrains, and looking forward to solve some puzzles today with all of you. Of course, I'm not alone. There's gonna be someone who's gonna be joining us, but I thought, we take a couple of minutes like we usually do. Just do a little warm up. Say hello, everybody. If you are tuning in, say hi. Very nice to already see a couple of familiar faces in the chat. And maybe just let me know how you felt about today's challenge. It's a whole lot of maybe pathfinding related stuff. Who knows? Did you feel like you had a good first approach? Did you code yourself into a corner this time around? Anything like that? Very good to see people. Also very good to see the little Christmas emojis that you're already throwing out here. Don't worry, the reading hat is with me. So just because we're in a different location does not mean we'll have to not have that one. Let's take a look here. Sadly, my day job was very demanding and I only did part 1. And I have an endless loop that I did not have time to debug. I can kind of understand that. Maybe when we discuss the solution, we can find something that might also, get you on the right path. That might be good. Today was the first time I had to do some performance optimization. Now, I'm curious here, Rob. Is this because you weren't happy with the execution time, or because it just didn't terminate at all? I'm curious. I just if you want to share more about that, it might be interesting to hear. People are already talking about things like elegant ways of detecting cycles versus maybe not so elegant ways by just checking if you've taken 50,000 steps, which that's I guess a way of doing it. Cycles are going to be a big topic that we're going to be talking about. Yeah. There's a lot of curiosity here. Some folks had the test pass, but did not have the actual input pass. It's going to be a lot of interesting stuff. So, folks, as usual, I'm just going to give you a very quick little spiel here. Because as you know, JetBrains and Kotlin by JetBrains are both very excited to be sponsors of Advent of Code this year. You know this by now because it is day 6, but make sure you join the leaderboards. Make sure you tag your repository, right? We can actually check that right now. And we can see that we already have 799. So if you haven't tagged your repo yet, make sure you do that right now, and you might become the lucky number 800. And whether you join our leaderboards and you're actually competing for the top spots, whether you're joining just to have some fun and compare yourselves, or if you're just tagging your repository and adding a bunch of things there, you are eligible to win some exclusive Advent of Code in Kotlin swag. So it's really worth it. Let me tell you, there's no other way of doing it. Of course, this is also, once again, the way to discover some things about Advent of Code, like our templates. And like the fact that we also have a template built on Amper, for example. Very nice. Okay, let's take a look here. Rob, 2 minutes and 45 for the initial solution. Okay, I'll be honest with you. In the mornings, I'd take a 2 minute and 45 solution. There was a year where I had a solution that I started, went to take a shower, found it to have just finished a couple of seconds ago. So like a good 15-minute run. So there's no shame in that, as long as you get the solution, right? We're gonna do a quick reload here. We're not quite there yet, but let this be the step. But, of course, so as usual, I'm going to take this off again. We're going to talk face-to-face here for a second. Even though I am in this lovely location, I will not be alone. In fact, I'm going to be joined by a wonderful guest who can jump in here, jump into frame, and introduce himself if he'd like to. Oh, is he making it? Hey!
Hello.
It's Martin. It's good to have you.
Thank you. Thanks for having me. It's very cozy in here. I really appreciate being back.
Right? You look very cozy as well.
Well, I tried. It's Advent of Code.
Yeah. It's the best reason to get dressed in a festive manner. You know, hang out, solve some puzzles. It's a good time all around. And yeah, like Max says, it's all about the stars. Did you get some stars today?
2 of them, yeah.
How'd you do that?
With Kotlin, you know?
Honestly, that's pretty good.
Also with Emperor.
Oh, nice.
My usual template is an Emperor. It did fail me once I cleaned up the solution because I needed a very new version of Kotlin, but we'll get to that.
Oh, I'm smelling some pre-release features.
Yes.
That's going to be interesting to look at.
I was worried. Like every day, the guests have something nice to show off, or you have a solution that uses like a guarded when statement or something, something super fresh. But today I accidentally ran into a scenario where I needed to use one of them.
Hey,
So it's perfect.
great. That's going to be exciting. I'm looking forward to that. We also have a visualization for today. Just going to throw that out there, courtesy of Victor from the Compose multi-platform team. So we're going to, stay tuned for that. We're going to investigate that a little bit. And maybe if there's a couple of small changes we might want to make to it, I'm not sure. We have Compose Hot Reload set up just for, that extra flair. Did you do all of these things when they came out, like right at 6 in the morning, or?
Almost. I was in a taxi at 6 in the morning, but I completed it like 30, 60 minutes later. I got to 2 stars before boarding, so.
Hey, and now you're here, and you get to talk about all these things. Isn't that great?
It is a break/continue inside lambdas.
Oh.
That is exactly what I needed.
Okay.
Spoilers.
Well, I'm excited. I'm excited to see it in action. So I think we can just dive into the problem for today by heading over to the Advent of Code website, and of course noticing once again that JetBrains is a sponsor of Advent of Code, and we are very excited to be sponsoring such a delightful event that provides you an opportunity to learn more about Kotlin, learn more about programming, about problem solving, about all of these things. So, with that, it is time for us to get the reading hat on. Reading hat goes on. You have your own reading hat?
I do.
This is great.
I'm not going to read, but I think I need it for the mood.
I think it helps with the problem solving, honestly.
Well, if I only had this at 6 a.m.
Yeah. It's sitting right on my bedside table. That's how I get there. Okay, with that.
Double the hats.
Yeah, I mean now, actually, yeah. I might have to grab this hat afterwards so that I can like stack them. That might get me to part 2 even faster. We need to explore the correlations there a little bit, I feel like. Okie dokie. It is time for day 6. Guard Gallivant. The historians use their fancy device again. This time to whisk you all. Just 2 seconds here, otherwise you can't even see what's going on. The historians use their fancy device again, this time to whisk you all away to the North Pole prototype suit manufacturing lab in the year 1518. Turns out that having direct access to history is very convenient for a group of historians. You still have to be careful of time paradoxes, and so it will be important to avoid anyone from 1518 while the historians search for the chief. Unfortunately, a single guard is patrolling this part of the lab. Maybe you can work out where the guard will go ahead of time, so that the historians can search safely? You start by making a map, which is your puzzle input, of the situation. For example, you have a little map. The map shows the current position of the guard with an up caret. It's right here, to indicate that the guard is currently facing up from the perspective of the map. Any obstructions, who creates desks, alchemical reactors, etc., are shown as hashtags. Lab guards in 1518 follow a very strict patrol protocol, which involves repeatedly following these steps. If there is something directly in front of you, turn right 90 degrees, otherwise take a step forward. Following the above protocol, the guard moves up several times until she reaches an obstacle. In this case, a pile of failed suit prototypes. So, moves up until it hits one of those hashtags. Because there is now an obstacle in front of the guard, she turns right before continuing straight in her new facing direction, heading over until she hits another obstacle. Reaching another obstacle, a spool of several very long polymers, she turns right again and continues downward. This process continues for a while, but the guard eventually leaves the mapped area after walking past a tank of universal solvent. By predicting the guard's route, you can determine which specific positions in the lab will be in the patrol path. Including the guard's starting position, the positions visited by the guard before leaving the area are marked with an X. In this example, the guard will visit 41 distinct positions on your map. Predict the path of the guard. How many distinct positions will the guard visit before leaving the mapped area? How many references did you pick up on this one?
So I only looked up one of them in real time here that you saw me Googling for. The very long polymers that the guard bumped into is 2021, day 14, apparently. I do have 2 stars on this, but I could not tell you whether I solved it without help.
I remembered, okay, so first of all, we have the device. That one is going for us from...
The links, yes.
Sure, that one's from here. The one from 1518, I think this one is the... Okay, that's weird. That's kind of not the link that I was actually expecting here. Because there is a problem, which is a guard moving around and falling asleep at a given time, which I believe we solved last year. I'm not entirely sure, but I think that may have been...
There's a 2018 day 4 problem? Is that
yes,
what's linked?
That's the one. Okay.
I skipped 2018 apparently, so I have no stars that year.
Okay, I do have some here. It might also be top of mind for some of you folks out there, because Eric Rustle did mention this in his keynote speech that he gave a couple days ago at the CPP conference that we linked yesterday. Yeah, apart from this, I also think like the long polymers are a pretty obvious one. The universal solvent is also one, but I don't exactly recall from when it was as well. Yeah, exactly. Maya says it just right. I listened to the Eric Wastel talk last night, and he said he chose 1518 so you can't use Unix timestamps, although that's only relevant for the previous puzzle. That's right. Yeah, the log entries of the sleeping guards, which was 1518. Exactly. Okay, well, I mean, the trivia aside, let's put the reading hats back off.
Oh, sorry.
Before you know, can't get too much solving power. Otherwise, you might overheat. What came to mind?
Well, it's a 2-day array. I figured, so there was an illustration here where the actual path of the guard was drawn. So one approach would have been to have the same thing parsed into a bunch of character arrays, and then I could have actually marked the path with an X like it does in the illustration. Mm-hmm. Easy to debug the test example as well, and then just count all of the X's.
Yep.
But before I started coding, I realized I might not have to hold this entire thing in memory. Because
it is pretty sparse, right?
It is pretty sparse. I don't know what it looks like for an actual input. It is
still pretty sparse.
Yeah, there's a lot of gaps in there.
Yep.
So I figured I can try this at least without holding it in memory. Just put everything into like sets and hash maps or something like that.
Okay.
And, see if part 2 requires me to hold everything in memory anyway.
Okay, cool.
Other than that, yeah, a bunch of offsets, some kind of direction that I can rotate as I'm turning right. I had a brief worry about whether the guard can face in different directions in the input.
Yep.
But I just searched for that character and it was in my input, so I ignored that completely. So the guard is facing up by default.
Yep.
I hope it's in all inputs.
I would very much assume so, since the other icon or the other character representations aren't even mentioned in the text. But yeah. Okay. Shall we see how you approach this?
Yeah. So I have 2 solutions that I brought. One of them is the code I've written at 7 a.m. at the gate.
Nice.
So I just want to, keep it real with the advent of code and show a solution that I'm actually using to get to the number that I'm going to submit on the site. I do not get up usually at 6 a.m. for this. I usually, whenever I wake up a couple hours later is when I solve it, so I'm not competing on the leaderboard. My goal usually is to have a decent enough, readable enough solution that I can push to the repo.
Now the question is, I do need to know this for full disclosure. Were you caffeinated at the time of writing this?
I was not at all.
Okay, see, now that's good info again. It's all comes together in the context. Great. So by the way, of course, from the setup perspective, we are using our fleet-based tooling for Kotlin here. And we are connected in collaborative mode, so you will be seeing my screen, but of course Marton is just going to be typing and moving around on his very own screen. But that's all gonna be wired together, so that shouldn't be any issue.
Yeah.
Okay.
Let's go for the first one.
Let's do it.
All right. So we have the input, parsed it with lines. Then we're going to have the obstacles that we can run into. So I've parsed that into pairs of ints. You can see here that as I'm writing code quickly, I really just want to be able to quickly create objects everywhere. So I'm just using 2, and everything's going to be a pair. And later on, I'm going to show you the cleaned up solution where I have data classes, where these things have names. But again, in the morning, when I'm trying to get through it as soon as possible, just to make sure that I do have a working solution and that I understood the problem correctly, I'm just doing pairs for everything. Because pair is already defined.
That's true. For me, that always already feels like a risk. Like the first thing I do, no matter what, is I'll just write a data class vec2 with like x and y, because pair int,
first and second.
It's
perfect.
First and second, I and j, like I like my x and y.
Yeah. So these are going to be most of our inputs for the puzzle, right? So the positions of the obstacles, x and y coordinates, and the initial position of the guard. Then I'm also extracting just the height and the width, because I know that I'm going to need it later to check whether they have left the room. Is it a room? The map yet?
Map. Property. Who knows?
Then the next thing that we're going to have is a bunch of directions. So by default, the guard is walking up, which is 0, -1, so no x change, and -1 in the y direction. And then these are all of the right turns. So this is again, I don't even write comments at that point, but this is up and right and down and left, essentially. And I just start at the first of these, which is up. Then we parse the inputs. So I just loop through all the lines. I loop through all the strings in the lines. Again, beautiful variable names for everything.
Amazing. Well, there's my x and y. I'm happy.
There you go. For each index, of course, so that we have the index as we're going through. And then we add the obstacles and we set up the initial position. Again, 2, very handy, very quick to write.
Yeah.
Real easy. Then we're going to have a position that also mutates. So I'm just creating a copy of that so that the position variable I'm working with is actually a separate one. And then I started writing this loop down here, which I think we can hop down to, and then we can see some of these quick local helper functions that I've defined.
Sure.
So the way that the guard is going to walk is as long as both of its coordinates, which are position first and second, are within the valid x and y values, we can keep looping. We need to count the number of positions visited, so that's going to be in a mutable set, and we start with having the initial position in there, although we don't need to now that I'm looking at it. That could be empty, but then we would have to specify the type, which is like a pair of whatever, so don't want to do that.
Sure.
Keep it inferred. So we visit each position, then we compute what the next position will be, and we check if the position we're about to step to is an obstacle. And did I just find the bug in here for the sample input? No, I don't think I did. Anyway, so we check if the next, oh, spoilers, sorry. So we check if the position we were about to step to is an obstacle, and if it is, we turn right instead of actually moving forward. Otherwise, we step forward. And these are all just super small local functions. So turning right looks like this. We had that directions array, and we just want to go from the current element to the next one and wrap over if we run out of the array. So we find where our current direction is in the array, and then we add 1 to it, and then we mod it by the size of the array, and that's how we step forward.
Mm-hmm. Yeah, that's kind of like ring buffery-ish.
Yes, exactly. Sure. There are real data structures for this, for sure. But that's not here or there. We could also keep track of the index that we're at instead of finding it with an index of all the time. But this works. Then the next position is super simple. We just offset the position by those direction offsets. So that's how we step in the given direction. And I mean, step forward is just taking that and reassigning. So these are just very quick helpers like that. And that works. I think it doesn't work for the sample input. I think I have a weird bug where it's off by 1 on the sample input. Now that I was looking at this loop, I was thinking, should I be checking if I'm stepping outside of the map here? But that shouldn't be, that is possible. I think that's what must be happening. That maybe I need to check here to see if I'm also stepping outside of the map with the next position. But it works on the real input, and it was just off by 1 on the sample. So
hey, great. Look at this, yeah, Rob, I think Rob's on my team here. Got so annoyed with the XY switching in my head that I just created a point data class. I'm exactly the same with vector too. Also loving this comment. I did part 1 uncaffeinated, and when I tried part 2, I started questioning my life choices. That's when you get that emergency brew. It
was a bit scary as always.
Yeah.
Do you want to go to your solution, or should we look at my cleaned up version of the same thing?
I mean, now that we have yours in context, I feel like we'll take a look at what yours looks like, and then we'll compare.
Okay,
because I'm not going to go through my early morning solution. I'm just going to go straight to the cleaned up one.
Yeah, makes sense. That's it. Yeah. This is the exact same algorithm, but it's wrapped into proper types for a change.
Look at this X, Y.
X and Y.
Gorgeous.
Yes. So we have a position, which we're going to use for a bunch of things, X and Y. We have a direction, which contains the offsets that you need if you want to apply that direction to a position. Mm-hmm. We have an initial direction in a companion object, because why not? So that we can go direction initial. Maybe that should be a val. Anyhow, and then we have a turn right. So on any direction value, we can just call turn right. It will do the indexing thing again. And wait, index of this, surely that's like ordinal or something, right? I think that's it. That saves us an index of.
Sure.
So yeah, that just rotates to the next direction, right. Then we have a nice operator here where we can add a direction to a position so that it offsets it using the direction. And then, because this is the fully refactored version, we have a helper function to actually run one of these loops, because for part 2, we're going to have to do that a bunch of times. So I have extracted the actual looping logic into a separate function, and both part 1 and part 2 are going to do the same looping with the same code, but with slightly different parameters.
Okay.
So this takes the size of the map, the obstacles and the initial position, which were our inputs. It has an initial direction, and it has this on new position visited callback, which is going to allow each part to process that we've stepped somewhere new.
Interesting. Okay.
And what we're doing in here is, again, we have the same two variables, the same loop. As long as we're within the map's bounds, we can go round and round. We have a callback whenever we visit something new, and otherwise we just keep running according to the rules of guarding. So we go to the next position. Well, we calculate the next position by applying the direction to the position. Then we check if we are looking at an obstacle in front of us, then we turn right, otherwise we just step forward. And the way that part one runs this is that it creates a mutable set of the initial position again. And whenever a new position is visited, it just adds that new position to that set. And then what we were asked to do is compute the size of the, how many positions we've visited on the map.
I like it. It's pretty elegant.
Yeah, I think that's it. And yeah, the main function is the same parsing logic, and then it just calls into part one. So we've already looked at all of that.
Nice. Awesome. Oh, this is a
and then
really
spoilers
solution.
for part two. It's just going to call into part two with the same parameters, just slightly different logic in there.
Can't wait to find out more about this. I want to throw up a comment here real quick. Just to make sure we retain a viewer here. I did part two in Gleam, brute forced with the Gleam OTP async tasks, which is just, you just spawn a bunch of new things on the OTP. You should stick around. You might be interested in how I solved part two of this problem as well. There's a very similar mechanism in Kotlin called coroutines that can really help speed up your code just a little bit if you can't really or don't want to tune your algorithm. So it's just a couple of lines of code, so stick around for that one.
Good note from Maya as well, that you could just pass in a range to begin with, so that you don't have to do width and height here, but you could immediately take an X range and a Y range, and then whenever you get to this part, you could just check like if position is in X range and in Y range. That would be nicer, and the same amount of parameters anyway.
That would be pretty smooth. Okay, input.indices. So,
True.
With that, let me show you what I cooked up. Slightly different, but I feel like we'll see some similarities. Let me find my main function. Okay, first of all, we read the input. This isn't anything special. We got some lines. That's all we need to start working on part one. You can see here, by the way, that I already tried to make like some assumptions and stuff to just understand about how big the input is.
Why would you need to do that?
Yeah, who knows? Who knows? But like, who knows how many things I'm actually supposed to do? Okay, so for me, I was like, okay, we have to run part one. All we need to do is we need to simulate a guard path given the lines using the logic, and then from this, I decided that I would return a result type. Which in this case, as long as the guard just happens to do like a run and then just exits, that's considered a success. Like, because that's just like, if you're done, you're checked out, you're going home. That's what I would consider a success. So if that happens, then whatever we get back from this function, which is a guard walk record, so that just gives us the information. Essentially, if I just take a look at the...
So this is a ledger of what the guard has performed.
Exactly. Which will be used to also calculate his wages. Makes sense, right? So our guard walk record is just a combination of the location that the guard has been at and the heading. And you can tell that this is, I think, a pretty similar modeling like you did. I have my vector2 class, and I have a plus operator, just like you did. And then I have a guard heading, which actually combines, which just stores the step, and then just has north, east, south, and west. I'll admit to you, when I was doing this morning, 6 a.m., I did write this part of the code, and I was like, okay, 100% brain power activated, because if I mess up one of these offsets, it's going to be really annoying to debug, because it's just one of those basic assumptions. I messed one up.
Which one?
That's a good question. I think south, maybe. I think I had south and east to just be the same, which was a little silly. And like looking at the outputs, I'm like, that's not a valid step, like pretty much immediately. So by the way, just as a short aside, I did create like a debug print thing, which just it just loops over the entire width, the entire height, and just creates some ASCII characters to show things. Helps a lot if you wanna briefly debug things. Okay,
and you do have this in memory, right? Like basically, it's a list of lists.
Yes, just a list of characters. We can see it right here. Okay, back into part one. So our guard walk record, that's just the entire receipt of what a guard has done. How do we calculate this? Well, we do a little bit of work. We create an initial one with the initial position, just like you did. I extracted this into its own little separate function that just finds a specific location. Nothing special here.
Nice use of the error function, though.
Thank you very much. Yes. So this is just because obviously I can't prove to the compiler that I will always find one of these characters, but I still want to return a non-nullable vector 2. So I do use the error function, and then thanks to the power of smart casting, it knows that anything below this is no longer reachable. Excellent point. From here, I decided, once again, this is something that came up in the previous streams. I'm just going to whip up a quick function called getTile, which is my shim to not directly access anything in the list of lists, but instead have a little bit of control over it. And you can see that I'm using this immediately, because if I just write the basic algorithm and I check for some coordinates, those coordinates might be out of bounds, and I just get an exception. Yep. This way, I just return a question mark character that's not yet bound to anything. So from that, we're doing pretty much the same loop like you did. We're going through the y locations and the x locations. So as long as we're in those, as long as we're inside the map, we'll try to take a step. We grab ourselves that specific tile, which is, again, just like that little function, and then we'll determine what that tile is. If it's a dot or our starting position, that means we'll do something here. We can skip over this specific part. That doesn't really matter for now. And then we'll just log, we'll just add it to our log, right? So our position and our heading will be added to our visited log. If it happens to be an obstacle, we turn right. If it happens to be a question mark, we're outside the map, we break. And that's our success result. That's it. Same solution for part one. Nothing super special here.
How do you interpret the result? Like, I assume you do a
We'll go back to that for a second.
Just check the size of this.
Sorry, let me hit my main function here again.
So
if it's a success, I'll just say, okay, everything that's in here, important part, distinct byte, because you might just be hitting the same part over and over again. You also have the heading in there. I think it's unlikely that you would hit it with the same heading twice, because I'm pretty sure.
You're looping.
Yeah, that sounds like you would be looping, which
is undesirable, because it would never end.
Yeah, that is undesirable. So we're going with the assumption here, obviously, that it's going to end. And then we calculate the size, count how many we have of those. Yeah, cool. So that's the first solution. Ideas?
No, that's pretty clean. I really like the ledger approach, because if part 2 asks you something like, have you been to the same part in different directions, or like, have you been to this coordinate before that one, or you have a full history of everywhere you went. So there's a lot of flexibility built into that.
I don't know who we're doing this bit for. Because I assume most people at home have maybe also tried it, or at least
not all of these examples were directly tied to part 2. Like it could actually be useful for various different part 2s, is what I'm saying.
That is true. That is true.
There's a lot, like, have you spent most of the time walking upwards? You know?
Yeah.
There are a lot of things you could compute from this data. It's nice to have it.
That is quite valid. Let's see what part 2 brings. I hope that we'll need to do some gravity simulation. I've already done it again. I don't know who this bit is for. So part 2. Reading hat goes back on. Can't be... Our producer also just reminded us of this, who you cannot see off screen. Just made sure the reading hat is on. And we are back for part 2. While the historians begin working around the guard's patrol route, you borrow their fancy device and step outside the lab. From the safety of a supply closet, you time travel through the last few months and record the nightly status of the lab's guard post on the walls of the closet. Returning after what seems like only a few seconds to the historians, they explain that the guard's patrol area is simply too large for them to safely search the lab without getting caught. Fortunately, they are pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place the new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab safe to search. To have the lowest chance of creating a time paradox, the historians would like to know all of the possible positions for such an obstruction. The new obstruction can't be placed at the guard's starting position. The guard is there right now and would notice. In the above example, there are only 6 different positions where a new obstruction would cause the guard to get stuck in a loop. The diagrams of these 6 situations use big O to mark the new obstruction, pipe to show a position where the guard moves up down, dash to show a position where the guard moves left right, and plus to show a position where a guard moves both up down and left right. Option 1, put a printing press next to the guard's starting position. Means guard runs up, right, down, left, hits the obstacle and loops. Option 2, put a stack of failed suit prototypes in the bottom right quadrant of the mapped area. So, up, right, down, left, up, right, down, right, up, right, down, and that's the loop. Option 3, put a crate of chimney squeeze prototype fabric next to the standing desk in the bottom right quadrant. You good?
The standing desk in 15,
Hey,
18.
They have to work ergonomically. What do you mean? With option 4, we can also put an alchemical retroencabulator near the bottom left corner. That's a good word to Google, by the way. There's only good content that comes up when you look that up. Option 5, put the alchemical retroencabulator a bit to the right instead, which puts it in this position, which once again creates a wonderful little loop that just happens to be quite infinite. And option 6, put a tank of sovereign glue right next to the tank of the universal solvent. So we'll have one over here, which once again creates a little bit of a loop down here. It doesn't really matter what you choose to use as an obstacle so long as you and the historians can put it into position without the guard noticing. The important thing is having enough options that you can find one that minimizes time paradoxes. In this example, there are 6 different positions you could choose. You need to get the guard stuck in a loop by adding a single new obstruction. How many different positions could you choose for this obstruction?
So I have not read, I have not read the entire thing apparently in the morning. Something that was new info to me was that the new obstruction can't be placed at the guard's starting position. This ended up not mattering apparently. But I definitely never checked for that part.
Interesting.
Did you?
Of course.
Of course.
I do pride myself in being vaguely able to read like diagonally. So I try not to skip entire paragraphs. I've seen videos of people just scrolling to the bottom and like interpreting like the question and like one example.
Yeah.
I think maybe in the first years I've done that, and I've hit my nose on those a couple of times. And while it is Christmas, I do not intend to look like Rudolph. So
Right.
yeah, I'm typically trying to.
Yeah, I think I skipped like one paragraph or so.
Luckily, it was not a big problem here.
Yeah, somehow this was not the problem where I was off by one, because that would have been an easy like off by one problem, but this wasn't it.
I might save some time not checking the obstacle location if the obstacle location is a guard starting position.
And that will technically be faster.
I mean, maybe. You'd have to benchmark it to really find out. Let's take a look at what you built for this, all right?
Yeah, we're gonna start with the initial version again.
Fun.
So basically, I took the entire code with the local functions and everything. I created a copy of them in within the same main function. This is all one file, one function. And I've nested my existing code in 2 for loops. So this is a brute force solution that goes through all possible positions without ignoring the guard's initial position. And it just adds whatever the current loop parameters are to the list of obstacles, and then it runs the thing with that. And then we have a counter up here where we are counting when we got stuck in a loop. So the only change in the simulation is basically the beginning of the while loop, because the part where we are determining the next position, checking for the obstacle, turning right, stepping forward is all the same. And what we are doing in the beginning of the loop is we have a visited variable, which is a mutable set of pair of int, pair of int. Thanks for scrolling. And so the first thing here is the position of the guard.
Sure.
And the second thing is probably the direction.
The position of the obstacle, maybe?
No, that's the direction. So because I've encoded directions as
also
the
as 2D
X
vectors.
and
Yeah,
Y
okay, that makes sense.
coordinates.
Oh, sure, yeah. Mm-hmm.
Yeah.
Perfect.
So these are basically the equivalent of your records.
Yes.
Right? Except this was the quick solution. This took me some time. So getting these right, I remember typing this out in the morning with the little closing angle brackets. That took some time.
I can believe it. Again, like this is the moment, even in the mornings, I'm starting to refactor because I'm like, there's no way I can keep track of this.
Well, it worked this time. So what I'm doing is, as we're going through, I'm adding each of these positions now tied to the direction as well, because I want to check if I'm standing in the same spot and facing the same way, because that means I'm stuck in a loop, because I've revisited the same thing, so that will just keep happening. And whenever this happens, whenever I detect that I got back to the same, not just physical position, but to the same state, essentially, which, by the way, like really nice like infix things and operators here. I think this is quite fun to write down.
That is very nice. You just quickly constructing a pair over here and then checking whether that pair happens to be in your collection of pairs. That's pretty smooth.
Like, you know, I guess the nice part would be like if the position with facing this direction is or something.
Sure.
We could iterate on that. Anyhow, that means we are stuck in a loop. So we break out of the current iteration and we go to the next one. So this just brute forces through the like 17,000 or so different coordinates that we had. That was about the space. I did check that part. I visually checked how large the map looks, and it didn't look that scary. And this runs in about, I want to say 5 seconds with brute force.
It's not so bad.
Yeah, uses small primitives, places them into a set, which is a fast lookup. So, yeah. And then again, I have a cleaned up version of this that we can look at. Just hopping back to this file, again using the same. I think you're not following me.
Sorry.
Yep.
There we go.
So again, we already had this run guard function that can simulate a run. So I just had to customize this. So what part 2 does is it will do the double loops. In each loop, it will maintain the set of visited states. We call run guard, which kicks off a simulation. we add that extra obstacle to the ones that we parsed from the input. And whenever we visit something new, here's the interesting part. Now we have a proper state for this, which encapsulates a position and the direction, because I did want a clean, readable solution as well.
Hey.
And so we created the state for the current position. We check if we've already been here, and otherwise we add it to the set. And the interesting thing that I ran into here is that I used to have a break here, which was breaking out of the while loop that was doing the guard movement. But now we don't have the loop here. We now have that in a separate function. So what I really need is I need to skip to the next iteration of this loop up here.
Yep.
So the current x-y combination has been tested. We need to go to the next y value. And so I can do a continue for that. And I'm actually doing this inside a callback. So this is a non-local continue.
Yeah, you have a lambda here that I suppose happens to, if we're clicking onto run guard, it happens to be an inline function.
I made it an inline function once I realized I have no way of signaling myself out of that situation.
Yep.
Otherwise, I could have wrapped this in one more function and returned from it or something like that, but...
Yeah, but so here we're essentially seeing one of the new features that are dropping as experimental in Kotlin 2.1. So we just turned that on. Here it's just our IDE that needs a tiny bit of time to catch up with us. So what this essentially does is, since an inline function, you can kind of treat as just copying the entire body of that, like into this location, right? Including all the code that lives in those lambda parameters. So when you think about it, like if the code's right here, you're not like doing some weird dispatch or whatever. Really, it's quite natural that you can return or break or continue from within this code, right? Like this code will be executed as part of this loop. Up until now, return was already supported, so you could have returned from the part2 function, but break and continue were there were little inconsistencies here, really, where you couldn't do this up until now. So now with the flag, that works, and you can break out from within a lambda from the enclosing loop, which, I mean, hey, good on you for knowing the feature exists. Maybe part of the job, and then like finding yourself in a situation where it actually is applicable. Very elegant.
It was great. I was worried about whether I'm going to be able to bring some interesting feature into the solution or an interesting API from the standard library or something like that, and I was like, I have a for each indexed, but like this was perfect.
This is a good fit. I like this a lot.
Yeah. And of course, if we want to try to break things, we can do a very brave inlining of this function. And I wonder if I'm able to do that. Select extra occurrences, apply. I think I'm stretching the limits of things here.
I think so too.
Yes, inlining is not available on that one.
Okay.
That's all right.
It's still
would have been fun to bring in the while loop somehow.
Still a little fresh, but you know, we're going to get there eventually as well. Let's take a quick look at my solution as well here.
Yeah. We saw something that we glanced over in your.
We did see something, and I think we can go straight back to that. So if we take a look at my simulated guard path, I mean the key insight you kind of already shared it, right? The key insight really is understanding that if you happen to find yourself in the same location with the same heading twice, then you are in a loop. Because naturally, like you only have one given choice. You don't make choices when you take corners. You always take right corners.
Exactly.
So you will necessarily, if you reappear at one position, then you will reappear at all the other positions in that specific loop as well. Or, of course, you can do the other version of this, which is just you can see if the path is longer than like 50,000 and just hope that, you know, there's not one really long path that happens to cover like every single field. I guess as long as the number is larger than all the fields, I think given that you have obstacles in it, that's not possible.
You can visit a field twice, but surely the size of the map is an upper bound for this somehow.
Surely. Anyway, this is exactly the kind of part that I have in here. I already have my little like ledger of all the things that the guard does. If it so happens that the guard record I'm trying to insert already exists, then it seems like this is going to be a familiar situation, which means we can stop. And I'm just going to return with an with a failure, which, you know, as typically you might do it in a result type. I decided to pick an exception, which is the illegal path state exception, which comes from Java AWT geometry, which don't use that one, but I figured the name's good enough. It is kind of an illegal path state because it's in a circle.
AWT didn't have like an illegal guard looping exception for you?
I did not find one in there, but it is an illegal path, so I decided I just returned that one. So with that, we can take a look at our main function, and here is where all the people using the Erlang VMs or Beam or Gleam or whatever else you might have might want to pay attention again. Because I was a little disappointed with how long this code took. Essentially, the code itself is pretty simple, right? All we want to do is we want to see we want to run for each obstacle position. We want to simulate that placed obstruction, which in itself just does a little replacement of the actual character. There's nothing special here. We want to see if that is a success or a failure. So if it's an infinite loop, we consider it a failure. So how did I do this in this case? Well, I used Kotlin coroutines because I wanted things to run ever so slightly faster. And in this case, all that means is I have an entry point into the world of coroutines, which is run blocking. I give that a dispatcher, which in our case is just dispatchers.default, which is just one of the dispatchers that allows us to offload tasks that are CPU intensive, right? Like you can just do work on these, and it's going to be a thread pool that kind of scales with the number of CPU cores you have available, so you maximize it without like starving the individual threads and so on. And then I just spawn a new task for every single possible location. I could also just do this using like async and await. So I could first I could actually get the results from each one of these and then calculate them together. But here I just did the summing up using an atomic integer. Again, everything that we have here in this launch is going to run on a thread pool of an arbitrary size, so I don't want to have race conditions. It's an atomic integer. I increment it if it's correct. Run blocking has the inherent property that it will wait until all the coroutines inside it are finished. So I'm starting a bunch of jobs. I am inherently waiting for all of those jobs to be done in this run blocking part, and then I'm just printing out the count. And I think this is maybe also some fun code to run here, because you will probably be able to notice a slight spike in my CPU cores as they get maxed out to 100%, and we see a whole lot of messages of this feels familiar. You can see that parts of this are certainly not super optimized. And probably I'm also just printing too much and copying way too many character arrays. But after just a little bit of time, we get a value, 1770, which if we do actually check back, that is the value that was my puzzle answer. So here I just had the opportunity to just take a very simple code snippet and in my case, make it like, I'd say, maybe 10 times faster than the regular single-threaded execution would be, just by throwing in a run blocking block, a launch, and making sure that I get my count in an atomic integer. Rob here mentions that I messed around with coroutines a bit, but it seems like parallel stream was at least as fast. That seems like it would be expected, because you're doing CPU-bound work here for the majority of the time, and all of that work also isn't like interrupted, or you're not doing any kind of I/O, not any kind of like quick switching between things. I feel like that's natural. So I could have also probably just spawned a bunch of threads instead. That could have also worked. I'm a little bit more comfortable with the Kotlin coroutine APIs in this specific case, but either works. And I just think it's a nice way to demonstrate that you can just have an entire code block, spawn a whole bunch of things, and then have it all come back together as regular code. You can see that none of the code that I wrote, I've never used the word suspend anywhere. I'm just using coroutines to fan out a bunch of work through my processors and then bring them back in. I really love this comment. This is my favorite comment, I think, that I've read so far today, which is someone on Reddit justified parallelized solutions by saying, I paid the full price for my computer, so I'm gonna use the whole computer. And I think that's an excellent way of thinking about it.
That's what I like to say. Wasted, like, empty RAM is wasted RAM.
Exactly, exactly.
What are we doing?
Yeah, true. So yeah, if you're like Miguel and you think this is cool, I do encourage you to learn a little bit more about coroutines. In fact, this is a great segue into a tiny little ad spot here, because KotlinConf tickets are still available, where you'll of course find a lot of people talking about related things to this. The KotlinConf CFP is also still open. So if you want to become a speaker at KotlinConf, you have 2 days left. So now is the right time to submit whatever talks you might have. And if you are interested in learning more hands-on, you might want to join my workshop, Asynchronous Programming with Kotlin Coroutines. Some tickets are still available for this. Or you might want to dive deeper into Kotlin multi-platform with Pamela and Konstantin. Or you might learn more about the web development with Ktor, with Anton and Leonid. Or, for example, you might also build shared UI with Compose multi-platform. With that guy over here, Martin, and with Victor,
Who gave us the visualization.
who gave us the visualization. And there's a whole bunch of other workshops here. But I think we should actually take a look at that visualization, because, I mean, we have it right, and we can see a little bit about, once again, how maybe what we've been talking about in the abstract this entire time.
Can I interject with 2 very quick things?
Of course.
So first, I stole your parallelization idea real quick.
Okay, I'm gonna
So-
follow you for a second here.
I copied the same exact structure, so run blocking, spawning off every run into just a launch. So I did this in like a minute or 2. And the only thing I had to figure out is what to do where I used to continue from this for loop, because that's now in a different coroutine. And the solution was to just throw an exception to terminate the current run and then just catch all exceptions,
It's almost like an illegal path exception.
which is very problematic, but it worked. And this gets the runtime from like 5 seconds to like 1.2, which is decent.
That's pretty big. That's pretty big. I think there's a good point here as well, which comes from Simon, which is that I think checking obstacle locations on the original path is a much bigger optimization. And you're absolutely right. This is...
Oh yeah.
But I think this is maybe something that is best understood actually by looking at the visualization. Not gonna lie, this is still a good segue. But yeah, of course it makes the most sense that you would only place the obstacles in a square that you actually reach. But that's not a great excuse for me to use coroutines. You are correct, and I think that is a move that, you know, we could have done. I'll be quite honest with you. This is not what I did this morning, and my solution terminated in a time that I was okay with. So this one, once again, it's all about what kind of goals you're setting for yourself. My data structures are not optimized. Again, if we just take a super brief look here, every time I place an obstacle, I do like a deep copy of an entire like pretty large array. Like I'm creating 2 new mutable lists. Like the entire thing is copied. There's a lot of low-hanging fruit here. If you enjoy those kind of optimizations, I encourage you to engage with that in Kotlin code and see how fast you can get it. Okay, let's take a quick look at the visualization.
Yep.
So once again, it's the same project that we've already seen previously, so I'm just going to start our hot reload version, but we can first of all just start by taking an actual look at what's going on. Our simulation, again, is contributed by Victor with minor patches from the two of us.
Who is the team lead for Compose Multiplatform.
Right, so that's quite exciting. So let me just re-trigger this, and we can maybe, if I slow this down just a little bit, we can see that indeed the guard walks, and every time she hits one of those squares, she gets sent to the right until she finally exits. And the same would happen on the slightly larger grid. I'm going to, first of all, zoom out just a tiny bit so we see a little bit more of it, and I'm going to reduce the delay somewhat as well. And now I'm just going to find the center point.
There it is.
Here we are.
Oh, they're running.
They are running.
Run away.
Thinking that was maybe a little too quick. This is not, obviously you can see there's quite a lot of elements on screen with this one. And we'll take a look here.
So all of these right now are individual boxes in columns and rows, lots of nesting. So we are really stressing out everything here. This could be, we could optimize this if the day was longer, and we could, you know, draw this manually on a canvas, go through all of that.
We just decided to take a couple of shortcuts.
I think with screen sharing as well, like this is slower than what we've seen in the afternoon when we.
That's very true. I'm just but
still,
you know, it's coming, and it's bound to hit one of those squares to send it upwards again. So that happens nicely. But we kind of get a pretty good idea here, and of course, you know, if we wanted to take a closer look at Simon's suggestion here, which is the optimization, right, of saying we'll only check whether it's in the path, it might actually make sense to like let this run for quite a while and then take a look at how many squares you're actually hitting.
Yeah.
Because if you're hitting most of the squares, it doesn't really matter. Like you're paying maybe with a slightly more complex algorithm that you might have to maintain for, you know, maybe having a 5% faster runtime. If it turns out that most of the runs, or that the typical run just ends after like a couple of tiny loops and 90% of things remain unvisited, then of course that's there's no point in modifying anything that's never visited in the first place.
Yeah.
So yeah.
And yeah, I mean, on the bright side, computing the initially visited path is basically instant. Like I think one loop of part 1 runs fairly instantly.
Yeah.
So at least pre-computing that for part 2 wouldn't be super expensive. So that's kind of pushing me towards putting in that optimization just because it sounds nice. But yeah, I would have to benchmark it as always.
Yeah.
Very satisfying though as it's chugging along.
Right. And you know, in the case of maybe this would also be a good opportunity to, for example, try out like notebooks like we saw yesterday. You know, you just throw up a quick visualization of all the fields that were visited. You get a quick idea of what's going on. And you still have quite an interactive way of seeing how many elements were actually visited. Or, you know, you could just print like the number of visited elements, which is literally
part 1.
Yeah, literally the solution of part 1.
Which was like 5,000, I think, out of
like 16,000.
So it was like 32%, 33%.
Yeah, so that's
you could optimize away a third of part 2. My solution might be 2/3.
Yeah, you could get like 70% out there.
Yeah, so my solution, if I use your threading thing with coroutines, might run in less than half a second.
Hey, I mean, look at this. We got some actual numbers for brute force. We got 12 seconds here from Zeltbrand. We have for only obstacles in path, that's 1.5 seconds.
Whoa,
which is
that's like, a lot faster.
Almost like 10 times as fast. That's quite wild. And then with coroutines on top, we go down to 0.5 seconds, which is, I mean, awesome. That's really cool.
I find it very interesting that only obstacles brought it down to like, I don't want to do public math, you know, but it brought it down by so much.
Yeah.
So it must mean that checking the positions that are not on the path is for some reason very expensive. Like it's very long runs before it runs out of the map or it terminates. I guess the puzzle doesn't generate in a way where, you know, like on the obstacle path, it's probably generated intentionally in a way where it terminates fairly quickly. But
Yep.
for others, it might bounce around a lot more, like 5 times as much.
And I like that people already have other opinion or other ideas on how to optimize this even further. With only storing the turning points as visited, optimize the solution even more. That's an interesting invariant there as well. And because the grid is about 16,000 blocks and the total obstacles in part 1 is about 4,500, so 75% reduction. Yeah, like the unique points that we end up visiting, which makes a lot of sense. Yeah, that's some good math here.
Yeah, and of course you could also optimize. Like obviously you don't have to step one by one. So if you have the whole thing in memory, if you write some helper functions, and you maybe set up a map or two, you could just jump to the next obstacle to the left from the current position and things like that, so that you don't have to, you know, loop through each step because you're really just waiting to hit a wall.
That's true.
So you could spare a lot of cycles there as well.
There's a lot of, I mean, these are the best kind of problems, I think, for a lot of our viewers, because I think there's a lot of folks who are quite excited about like getting those numbers down. But again, the beautiful thing about Advent of Code is you kind of get to set your own goals. You get to, if your most important quality is that the code is super short, like if you want to go optimize by tokens, you have like physically the shortest solution, that's a move you can do. I'm not sure if you can do this as a Kotlin one-liner. It would be surprising, but maybe.
I'm sure someone has a single expression solution at least in the channel.
Potentially, why not, right? And if you want to have the fastest solution, great. If you want to have the solution that you feel is the most like object-oriented or most functional or doesn't use a single mutable variable or mutable collection, all of those things are great. If you want to try out new things like persistent collections that we have in Kotlin as well, which are under I can just pull that one up real quick here. We have, for example, the Kotlin X collections immutable, which is its own library that you can use that provides persistent collections that you can modify without having to copy the entire thing on operations. So it's a more performant way of working with truly immutable data structures, which is quite exciting. There's tons of different like options. If you're saying this is the first time I'm touching coroutines, or this seems like the first time I should be touching coroutines, it's a great opportunity. There's just so many things that you can do with it. I want to just try one thing here, and again, this might not be quite fair towards our not so optimized simulation, but we can also fire the solution at like max speed, which now makes it look like it's more of a bullet zooming around with a lot of things. I think at this point, it's really just constrained by our slightly unoptimized rendering code here. But we can very quickly see how much of the grid gets covered.
I mean, we can hot reload ourselves out of this if we want to. So we could. Sorry, I've lost the correct project. I think I might have closed that window accidentally. I think I did.
Which window?
My fleet window.
Oh.
That's on me. Let me try to just very quickly reconnect. Oh, I minimized it accidentally. There we go.
Oh, look at that.
So I think we could just get rid of the animated part and then it should run faster, right? So
likely.
We have.
So as we can see here, by the way, I think we've hit. Did you already make an edit?
Not yet. So there's the padding is fixed. I think it's just the graphics layer that we want to remove, right? That sounds about right.
That does sound about right.
So we remove that. We save. Oh, you're beach balling.
I was already beach balling before you started typing here.
Okay,
I
so we're
think.
not gonna hot reload ourselves out of it because.
Okay.
Because graphics layer is a lambda and it changes the offset of lambdas. Yeah.
Fair enough. We can still
Makes
rerun this.
Supposedly we've removed an animation now, so I think it should be.
So if we switch to.
Oh, we can also remove the launched effect
Sure.
entirely. I think that compiles. Yeah.
Okay, and I'm zoomed out all the way, and I should have turned off the delay in the beginning,
Phew!
and now we can really see this
There we
thing
go.
fly a little faster. There we go. So now we get a pretty good
I bet
idea.
the stream can't keep up with the frame rate of this.
It's, yeah, surely, right?
It kind of can, apparently.
But yeah, look at that. We get ourselves a good idea of how that code might run. Yeah. Very cool. So I have to say here once again, first of all, Dave, thanks for coming on the show, and thanks for tuning in for these later days. If you haven't seen the stream that we did with Dave, make sure to check back on that one. But also, yeah, these visualizations are great. Huge thanks again to Victor, who's the team lead of Compose Multi-Platform, who provided us with the scaffolding for this. And then we introduced a bunch of performance regressions.
Yeah, it's what we do.
Yeah, but they did have some cute animations as a result. So
Again,
yeah,
it's what we do.
it is what we do. So yeah, awesome. I mean, what else is there to say?
Yeah, I think we've probably exhausted this problem, but it was a fun one. I'm glad it was. As always, I'm glad I was on for day 6, because this was still a very solvable problem, even being in transit and waking up super early for that, and with all of those things involved. Yeah, I think we delivered very neat solutions, and again, just love the visualizations.
Yeah. So I of course want to say thank you everybody for tuning in, for being with us, even on day 6 of Advent of Code.
On a Friday evening.
Yeah, no less. And yeah, I'm so excited. I'm so excited we get to do this year. I'm so excited you were here in person.
Yay!
This is a very unique format. I'm so excited we have a nice fireplace in the background. I'm gonna warm up afterwards in the virtual.
It is very warm in here.
That pixel radiation. Gotta get that. Yeah, but I think we've done a great job. Congrats to everybody who also decided to do some puzzle solving today. I do want to check one final thing here. And I think that one we throw it back on screen. Look at that. We've cracked the 800 public repositories that are tagged with AOC 2024 in Kotlin. Whoever you are out there, you are appreciated. And so are all the other 799 of you who've done this. If you haven't uploaded your solutions yet and tagged them with AOC 2024 in Kotlin, now is the time. It is the way to get some cool Advent of Code swag, potentially.
Do you want to quickly show just the tagging thing?
Absolutely. Let me do that for a second.
Just to make sure that anyone...
Of course. We'll do that. I'm going to pull up my AOC 2024 behind the scenes here. What you do, you head on over here, you hit the little gear icon under topics. You'll probably not have anything. So you just hit AOC-2024, and you don't do in Dino. You do in Kotlin. Did I do it the right way around? AOC 2024 in Kotlin. So this one.
That sounds right, yeah.
And you submit. AOC-2024-in-Kotlin. And that brings you to that wonderful public repository collection here. Awesome.
Tomorrow is Saturday, so it's going to be a tough one. Oh no. That might just be.
We will see.
And importantly, you're going to have an early stream tomorrow.
That is very true. If you haven't yet, make sure you click those little notify icons. Those are, of course, on our youtube.com/JetBrains. Not just /JetBrains, /Kotlin. You can tell it's getting late. So make sure you go to that live tab and you hit notify me for the remaining streams so that you don't miss them. Again, tomorrow in my time zone, it's going to be 2 p.m. So make sure you check in a little earlier. It's going to be interesting. For me, the jury's still out whether it's going to be a harder problem or not.
Harder problem last time to prepare for the stream. Should be good.
We'll
Saturday,
see.
though.
I mean, hey, maybe Eric has some, maybe he has a little bit of compassion with all of us out here who are streaming in much less time since the release. But it is worth checking in because I have a weird feeling you might see some visualizations again tomorrow. It's gonna be a recurring guest. You can already start guessing if you'd like to. But yeah. So thank you so much, everybody. Decided to tune in. Enjoy your time until the next Advent of Code puzzle unlocks, where you get to do a little bit more Kotlin. So yeah, thank you, Martin. Thank you, everybody at home, and take care. Bye-bye.